This week, as I was driving my daughter to school, we had a conversation about daylight savings time, and she was expressing confusion about how it works. And I admit, I recall myself at one point sitting down and carefully working out, okay, what is this daylight savings time thing? How does it work? And eventually I decided, okay, it's something like adding a periodic square wave to the time coordinate. Well, I didn't try it.
I could work on this, that's right.
So my point is that any change in the usual notion of time is very hard for us to understand somehow. We're very fixed to the way we typically think about time. And so what I'll do today is just say some things about some results about perhaps about the nature of time that I've run across in the quest to build a quantum theory of gravity. And so, in particular, I'll try to describe a way of thinking about time in terms of unfolding of the process. I didn't use an article in my title because I didn't want you to think that there's necessarily just a single process that would describe the universe. So, but what I really mean is something like a quantum process. But I don't know exactly. I don't know exactly how to describe a quantum process. But the idea is there will be some process that is a multi-fingered character and would involve not necessarily a single history, but perhaps a set of histories. So I'll start by introducing the basis of the approach, which is on causal sets, which we heard a little bit about this morning. And then I'll describe a dynamical law for causal sets, which is based on a process of growth of the universe. And then I will present a number of results of a sort that have arisen from thinking about time in this way, which may be of interest to this audience. And then, in particular, I'll talk about a way of expressing a quantum dynamics for causal sets in terms of an action entropy, and wrap up with some conclusions. So, in 1978, Gerard Tufte won the Nobel Prize for the electroweaving theory, wrote an article about quantum gravity, in which he mused about how one would attempt to write down a theory of quantum gravity. And it goes on for 10 plus pages describing his thoughts. And then about three pages before the end of the article, he shifts gears and talks about how one might try to write down a lattice description of gravity. And he essentially outlines the causal set approach in that article. And so he argues that we should take the lattice discretization seriously as a model for gravity, that maybe the lattice itself is somehow telling us something about space-time geometry. However, the metric tensor is difficult to define on the lattice while respecting covariance. And so a simpler concept, which is invariant under the Lorentz transformation under the theory, is the causal ordering. And so the idea is to build a theory based on causal ordering. In the discrete language, in the context of discreteness, this can be mathematically represented as a partial ordering. And so the idea is that this partial ordering itself defines the lattice. So the lattice is just going to be a set of elements of, you can think of them as atoms of spacetime, elements of the causal set is the word I usually use, which is endowed with a partial ordering, which is has the physical meaning of causal ordering. And so then the idea is that the consistency of the causal ordering of the discrete lattice with the continuum gives a relatively precise correspondence between the discrete structure and the continuum structure with which we're more familiar. And then furthermore, he proposes that the early universe should emerge as something like a tree which begins from a single element and grows in some very rapid rate. So before I describe the theory, I just want to say a few words about how I think about it. So the idea is I want to write down a model. We want to write down a model for which we expect to describe the gravitational interaction. Hopefully this will be a simple model, because in general simple models are better than complex ones. So I'd be surprised if it's a theory of everything. I don't particularly expect that this will give rise to a theory of everything. And I'm not entirely sure whether it's fundamental. Maybe you can tell me your comments on whether it could be a fundamental theory. But again, the goal is to give a quantum account of the gravitational field. Of course, we hope to get more of this. We hope that some portion, for example, some portion of the standard model comes out of the theory. But at the outset, the real goal is to write down a theory which gives a quantum description of gravity. So the attitude behind the approach is based on the writings of the Japanese philosopher Kaketani, who described the process of theory construction or model building in terms of 3 stages, which form a cycle. So the first stage we could regard as the phenomenological stage. So what are the phenomena which the theory should explain? And then once that's identified, a second theory is a kinematical stage, in which one decides what is the fundamental mathematical structure which will be used to build the theory. What is the mathematical underpinning of the theory? And then the third stage is the dynamical stage, in which we decide what are the equations of motion of the substance. So the kinematical stage decides what is the substance of the theory, the thing that we're trying to describe, and the dynamical stage describes the substance. And one point I want to make is that it can be important to spend a fair amount of time thinking carefully about the kinematical description of the theory. It can be useful in guiding how the process proceeds. Okay. So, what is a causal set? So the causal set is, as I described, it's a set of atoms of space-time, if you like, which have a partial order defined on them. The idea is based on the observation that causal structure is a very rich structure. So there's a theorem by David Malamud and similar ones by others, which show that which prove that for a reasonably well-behaved space-time, one can recover the space-time geometry up to a conformal factor just by the causal structure of that space-time. So there's a lot of information encoded in the causal structure. And the second is the need for discreteness, which Sarah observed as well. So the theory is going to be defined in terms of a set, which you can generally think of it as being a countable set, which has a partial order defined on it, which is simply a binary relation, which is irreflexive, transitive, and locally finite. So locally finite just means the set of elements y between any pair x and z is finite. And on the right, this is a Hasse diagram, which we've seen earlier. The edges, the lines in this diagram represent relations, such that the earlier nodes are drawn below the later nodes. And the relations which are implied by transitivity, so for example, I know that x precedes y in this causal set on the right. I don't draw that explicitly because it's implied by the existence of these intermediate relations, which I'll call links. So those are relations and links. The chain is a totally ordered subset of the causal set, a subset in which every pair is ordered of the relations. An anti-chain is a subset which has no relations among its elements. The height of a causal set, this will be an important concept for recovering some notion of time from the theory. So the height is the length of the longest chain. And the width, analogously, is the cardinality of the largest anti-chain. The notion of a causal interval or an order interval is sometimes useful. It's, as we've seen earlier, for example, the set of elements between x and y forms a causal interval. And furthermore, maximal and minimal elements are useful. Maximal elements have nothing to their future, and minimal elements have nothing to their past. So I've given a precise mathematical description of the fundamental objects of the theory. That's the kinematical structure, the causal set. But in order to understand what it means, what are these atoms of space-time, I need to say something about how to connect that with everyday experience, or if you like, the experience of a theoretical physicist working on quantum gravity. So the idea is to describe describe a correspondence between the discrete and the continuum in terms of an embedding. So an embedding is an order-preserving map from the causal set to a space-time, which is phi here. So two elements are related in the causal set, and their image points are related in the space-time. The faithful embedding is one which furthermore preserves the correspondence between number and volume, which means that the number of causal set elements which get mapped into some region of space-time is a Poisson random variable whose mean is V, where V is the volume of that space-time. So that gives you an idea of in a sense, what I mean by an atom of space-time, or an element of the causal set. And then furthermore, the space-time cannot possess structure at scale smaller than the discreteness scale. So the idea then is that the causal set itself is fundamental, but this correspondence with the continuum is necessary so that you understand how to think about the causal set. What does it mean physically? And so the idea is that if there exists a faithful embedding from the causal set into some space-time, then we say that that space-time is a good large-scale approximation of the underlying causal set. And so this is a picture of a causal set which arises from sprinkling into a region of two-dimensional Minkowski space. The points are just given by a Poisson process in this square region, and the green lines represent the links in the causal set.
Poincare invariance comes out of it? Is it Lorentz invariant?
Yes, so this is, the sprinkling into the entire Minkowski space is Lorentz invariant. And so why is that? Because it depends only on average. So it depends only on the volume. The description of the lattice, depends only on the space-time volume, which is an invariant quantity. So by contrast, on the right here, I've drawn another sort of lattice. So the red points describe a regular diamond lattice, if you like, in Minkowski space-time. And the green points represent that same lattice, viewed from the highly boosted observer. So there it's pretty clear that this lattice is not Lorentz invariant. So it turns out that a random lattice is Lorentz invariant. Okay. So we can already say some things about time, about clock time, from what I've told you so far. So the idea is to recover something like a time-like distance you measure using a clock from the causal set. So we know that in special relativity or general relativity, a time-like geodesic is an extremal chronological curve. And so note that because of the Lorentzian signature, the extremal curve of interest is in fact the longest curve. So if I want to know the proper time separation of two time-like related events in space-time, then I look for the longest geodesic which connects them. And so the idea is to do the analogous thing on the causal set and look at the length of the longest chain connecting a pair of points x and y as giving the time-like separation. So this is a picture of the set of all longest chains between a pair of points and the sprinkling in Minkowski space-time. And so you can see the set of longest chains highlighted in blue here. And then by a theorem of Brightwell and Gregory, we know that this length of the longest chain is proportional to the time-like separation of these two events in the limit of large density of sprinkling. So now what about dynamics? So first thing you might think about when writing down a dynamical law may be to think in terms of Hamiltonian evolution. So the Hamiltonian is a generator of the time evolution of the system. However, when thinking about quantum gravity, it's difficult because, well, for example, we don't have a preferred notion of time. So in order to avoid questions of that sort, it seems natural to turn attention to the Lagrangian formulation of dynamics and then to integrate the Lagrangian to get an action. And so later on, we'll do something rather like that. So the idea is to write down the dynamics in terms of a sum over histories. So if we want to think for a moment about a classical stochastic theory that assigns a probability p to every history in the space of histories gamma, then I can write down the probability of some event in the sense of probability theory, the subset of histories. Probability of an event is just the sum of the probabilities of each history in the set. The quantum theory, then we can use something given by Feynman. We can describe an amplitude with the history gamma given by the exponential of the action. And then we can do something like write down the probability of, again, an event, a set of histories, in terms of some sum of this form, which is a combination of the coherent and incoherent sum of the histories. And the idea then is to write down something like a quantum measure to describe the dynamics in terms of some quantum measure on the set of histories of the theory, and which will look something like this. It comes from the Feynman description, where there's something like a final delta function at some truncation time t to give us a unitary, to maintain unitary. But of course, we don't know what the exact form of the equivalence function of the quantum measure for gravity should look like. That's why I did the quotes here. Okay, so since the quantum theory is complicated, let's go back and just think about the classical theory, but in this case, a classical stochastic theory. And to get you in the mood for it, imagine the simplest possible dynamical law, which is just to take all the histories, put them in a bag, and then pick one out at random. And so if we do that for the set of coin tosses on 40 coins, this is the fourth sample histories that you might get of coin tosses, 40 coin tosses of a coin. And what I want to ask is which is the typical sequence? So which sequence might you expect to arise when you pull one of these out of the bag? Does anyone see?
Well, I know two of them that it's not, but...
the one, yes. The one is a typical. So now we can do the same thing for more complicated structures such as a graph. So take the set of all simple graphs on n nodes, put them in the bag, pull one out at random. Which sort of graph would we expect to see? This one? Well, it looks different, sure. It's hard to see in the picture, but the idea is, so the edges are between nearby nodes. So this has some structure which is not generic in that sense. So the idea is so it will come out as an Erdos-Renyi random graph with probability p equals a half, for finite. If the number of nodes is finite, so that would be the second here. And so maybe
Why isn't it black?
well, this is something close to the complete graph. Yes, it has many relations, and as n gets large, it will look more and more like that. Okay, now what if we do this on a partially ordered set, finite partially ordered set? What's the typical finite partial order look like? It turns out the answer is surprising. It's in fact the bottom object. So it seems to have a very regular structure. It has 3 layers. It's very close to n over 2 elements in the middle layer. It has close to n over 4 elements in the top and bottom layers. And then a bunch of relations next to it. So it turns out that there's a theorem by Feynman and Rothschild that as the number of elements gets large, almost every partial order is over this form. This one is something like a sprinkling into the Minkowski spacetime, and the others are different ones. So the theory faces a big challenge. How can we get something like a spacetime, which we've seen, we expect to look something like a sprinkling into Minkowski spacetime, out of the theory in which almost every history looks like this. In fact, a super exponential number of these histories dominate in the super exponential form. So you might be concerned, how can a locally defined action ever overcome such a dominance of these Rothschild partial orders? So now I'd like to say some words about dynamics. So a different approach to writing down the dynamics, and one which is based on a process, which I started with, of sequential growth. So the idea is to write down a dynamical law for causal sets, a stochastic dynamical law, in terms of a growth process, in which the causal set grows one element at a time, beginning with the empty set. So the idea is that this is a stochastic process. In fact, it's a Markov process if you regard the entire causal set as a state of the Markov chain. And the probabilities are based on three principles. So if we didn't place any restrictions, if we just wrote down the most general stochastic law of this form, it would turn out that there's an enormous number of possible theories. And so in order to get something reasonable, we have to impose some physically motivated conditions on the set of possible dynamical laws of this form. So we impose three conditions. One is internal temporality, which is that the causal set grows only to the future. So this is some hint of the, well, I'll get back to it. The second, which is going to be very important, is discrete general covariance. So this condition, the idea is that the probability of arriving at any finite causal set should be independent of the order in which the nodes of the causal set arose in the growth process. And so we call this discrete general covariance. And the third we call Bell causality, is a causality condition which is intended to reproduce a notion of causality which would violate the Bell inequalities. But it's perhaps reasonable for a classical theory. And so the idea is that the sequence of the growth is, in a sense, erased by this discrete general covariance condition, although there's some shadow of the sequence which is maintained in this internal temporality, which is seen later. So this is a picture of the growth process. This is a diagram in which the diagram of topo set of finite causal sets, where I've drawn an arrow between any pair of causal sets if the upper causal set could arise by adding a single maximal element to the lower causal set. So any upward directed chain in this diagram or path describes one growth process of the causal set. So for example, the blue path here is one particular way of growing this 5-element partial order.
What are the symbols on? What are the symbols on nodes then?
Well, the symbols are decorations that I could describe. In fact, Chris had a lot to say earlier about the. Well, you can ask, for example, well, it's interesting. So you can ask, for example, how many ways are there to go from this causal set, this 4-element causal set, to this 5-element causal set? And it turns out that you can think that there's two, because the new element that arises is this rightmost maximal element. And so it's to the future of this disconnected element and one of these two other maximal elements. And so which of those two does it choose? So there's two different ways to do it. So that's the two. And then these Q's are transition probabilities. Okay, so it turns out that you can, just given these conditions, you can write down a relatively unique family of dynamical laws of this form, which gives it the probability of a transition from an n-element causal set to an n+1 element causal set. And the expression for these transition probabilities is given by, well, it includes some quantities, phi and m, which are order invariants of the past of the newborn element, which gives rise to the transition, and furthermore a collection of free parameters, in fact an infinite sequence of free parameters of the theory, which you can think of as analogous to coupling constants a standard model. So these are parameters of the theory which are not determined by the principles you can also support.
So
Which are non-negative in the parameters.
this is an infinite number of free parameters, this theory.
Yes, it's infinite.
So in what sense is it constrained? By anything?
Yeah, so it sounds like a big number, and then...
So I'm just a dumb physicist, I can't understand really big numbers of coupling constants.
Yeah, so David points out it's only countable. Which in a sense isn't so bad. So a simple thing I could say is that the observable universe is finite. Well,
As far as we know.
as far as we can see. So,
Very clear.
in that sense, it's finite. But maybe a more important thing to say is that, well, I'll get to it later, but there's a sense in which there's only one sequence of parameters, one parameter family of sequences which are relevant, which after a long time, if you wait long enough, then only one parameter family of sequences is relevant, and that's given by this transitive percolation dynamics. Where the Tn is just given by this one parameter P, which is a probability between 0 and 1. So Tn is just this combination to the end. So transitive percolation is a very simple model. The idea, so P has a very simple meaning. If I take any causal set, say this, we'll go back to this 4-element causal set, and I add a new element, I want to work out the probability to go to this 5-element causal set. All I do is flip an unfair coin, a coin with the key, once for each element, and then draw the new element above all the ones that for which I got heads. And take the fast closure of those points so that it maintains transitivity. So, before I go on, I want to just give a brief outline of some of the results that come out of thinking about time and gravity in this way. So some which are based on the model as I've described before, and some which are quantum in a sense that I'll get to in a moment. So one is that the model gives rise to a cyclic cosmology with something like evolving coupling constants. So these Tn evolve under the cyclic cosmology. The second is that it gives rise to a de Sitter-like early universe. The early universe of this model is a de Sitter-like behavior. And a third is that you could think of, okay, so complex networks is another field. It's the science of trying to understand networks such as the internet, which are ubiquitous in the real world. It turns out that this sort of thinking can give rise to something like an internal time in the universe, so there's sort of an intrinsic notion of time, which is separate from the external clock time we're more familiar with. Okay, and then I'll talk about a quantum approach. So the quantum approach will be based on, again, on the sum over histories on the Feynman path integral. And so we can ask some questions which are relevant to time of that approach. So one simple question is, when do the Feynman-Rothschild causal sets dominate, these 3-layer generic partial orders? How large does n have to be in order for them to dominate the sum of the set of histories? The second question you might ask is, are almost all histories roughly time reversal symmetric? So if the set of all histories is really described by the Feynman-Rothschild orders, then you might ask, are they all time reversal symmetric? The third question, is the dynamics able to escape from the Feynman-Rothschild partial orders? So if we impose a reasonable dynamical law, can we get something which gives us something other than these very degenerate causal sets? And then, is there current observational evidence which is hinting at a way of thinking about quantum cosmology at this point? So transitive percolation, it turns out, is fairly simple to understand. It's a completely homogeneous model where the feature of any element is independent of anything space-like to it. However, due to random fluctuations, it's inhomogeneous in time. And in particular, there are theorems which prove that there's an infinite number of posts. And there's some results on the size of these intermediate regions for the transfer percolation dynamics. And so after one of these posts, we get something which is described by an originary dynamics, which is simply a transfer percolation conditioned on the fact that each new element is the future of the post. And so if we think about it, the universe expands to a volume of something like 1 over p for one of these posts. Which I'll get to more in a moment. So the theory then gives rise to something which we call cosmic renormalization. So the growth dynamics is formally Markovian because the entire past history is taken as a current state. However, it has a long memory. And so the idea of this cosmic renormalization is that you can describe the growth in terms of cycles of the universe, where each cycle is described by some collection of these coupling constants, Tn. And it turns out you can describe the sequential growth dynamics in terms of an effective dynamics in each of these cycles, which is given by a particular sequence. And these sequences get transformed by a cosmic renormalization process, as we call it, under subsequent cycles of contraction and expansion of the universe. And then it turns out that there's an attractive fixed point of this cosmic renormalization process, which is in fact the transfer percolation dynamic. So in this sense, the transfer percolation is a natural attractor of this renormalization for the dynamics. And then for this particular sequence, Tn is given by this formula, which results in there's an infinite number of posts. So back to the originary percolation. So in the limit where p is very small, but nevertheless we condition on the case that each new element appears in the future of the post, then we get something like exponential expansion. And so we get something like that expands very rapidly from the post. However, we don't get something which is exactly space-time manifold or GR. So this is a picture of an originary percolation causal set. This is a picture of a much larger realization of originary percolation. And so it turns out that this causal set is de Sitter-like in the sense that if you look at the number of elements in every order interval of height L, and you plot that as a function of L, you get something which is not so dissimilar from what you'd expect from big plus one-dimensional de Sitter spacetime. So the internet, so now network science. So network science is the idea is to describe the structure of networks which are ubiquitous in the real world. And yet, part of the goal of this the goal is again to write down a theory, write down a model which describes these networks in an effective way. And so one of the models of these networks is based on something very similar to what I've described. It's based on a sprinkling, again a Poisson random process, into not a Lorentzian spacetime but a Riemannian manifold. So this is a picture of a two-dimensional disk within the H2 within the hyperbolic plane. And the idea is to connect any pair of points whose distance is less than the radius of this disk. So this yellow point here connects to these. So because of the structure of the hyperbolic geometry, this yellow point connects to these points here by the red, describe the red lines. And so on. This one connects to many more because it's closer to the center. So it turns out that this model bears a striking resemblance to the model of the sprinkling of the causal set into the Sitter spacetime. And the idea is that, so this is a picture of a hyperbolic disk, and this is a picture of the de Sitter spacetime, the Sitter manifold around it. So the idea is that one can write down a simple mapping from the hyperbolic disk to the de Sitter spacetime, such that the nodes in the hyperbolic disk get mapped to points in de Sitter spacetime, and the connections described by this model that I just described, this diagram, are given by the causal relations of the de Sitter spacetime. And so this is one interesting feature of this is that in the de Sitter spacetime we have, of course, a notion of time. So the notion of time in the Lorentzian spacetime. And so under this mapping, it suggests that the radius, which is implied by this model of sprinkling into a hyperbolic geometry, is capturing the notion of some intrinsic notion of time in the de Sitter spacetime. So there's some sense in which there's a time, an intrinsic time in the internet. Okay, so now I want to talk about the last few minutes about the quantum model. So the idea is to write down the Lorentzian functional integral for gravity. So it looks something like this, where we have some expression for the Einstein-Hilbert action for gravity. In the case of causal sets, this becomes much simpler. It's simply a path sum over causal sets. And yet we can make it simpler, further simpler by restricting the sum to causal sets of fixed cardinality. So if we have an effective expression for the Einstein-Hilbert action for causal sets, then we can write down a path amplitude. And so the idea is to write down something which is based on the discrete D'Alembert. So one can write down a D'Alembert operator on a causal set which mimics the behavior of the D'Alembert in the continuum, which I'll explain in a moment. So the idea is quite simple. If we have a point, an element x in a causal set, and I have a scalar field, phi, defined on the causal set, it's just a map from the causal set elements to the real numbers, say. And I want to write down an expression which behaves like the D'Alembert operator on that point. And it turns out to be a fairly simple sum over the field values of the causal set elements to the past of x, where there's a weight which goes into the coefficient weight, which depends on the layer of how far, essentially how many elements are there between the candidate element y to the past of x and x. So layer 1 are the set of elements that are linked directly to x. Layer 2 are those which have exactly one element in between. And layer 3 are those that have two elements in between. And one can do an analogous thing in 4 dimensions, and one gets a similar sort of expression. If you want to know what this looks like for large density, this is the same picture, but for very large sprinkling density. So just to give you some idea of the intuition for how this would look like for large n. So these are, again, the same layers, the same 4 layers to the past of the element x. So then the idea is that in curved spacetime, one can show that under certain conditions, one can show that in the limit of large sprinkling density, this D'Alembert operator that we wrote down, its excitation value, averaged over sprinklings, gives rise to not just the D'Alembert in the continuum, but the D'Alembert minus the curvature correction, which is proportional to the Ricci scalar in that spacetime. And so if you apply this box operator in the causal set to a constant function minus 2, then you can get something which you expect to be proportional to the Ricci scalar. And so then using this, one can integrate this sum over the causal set elements and get an expression for the Einstein-Hilbert action on the causal set, where the terms in this, the action is very, very simple. It's just an alternating sum of terms with some alternating coefficients. For each of these terms is just the number of order intervals of a given cardinality. so then using this, we can write down an expression for the partition function for causal sets. So here's an example of how to compute the. Here's an expression of what these terms are for very simple 6-element causal set. You just count the number of order intervals of different cardinalities. And then, so the usual way to handle something like this is to do a Wick rotation, where t gets rotated to imaginary time. But in the case of causal sets, we can't do exactly that, so we do something similar, which is perform an analytic continuation in an arbitrary coefficient beta at the point of the action. So then doing this, we can cast the theory in terms of the Euclidean sum, which can be analyzed using the Sharpless-Monte-Carlo. So what are the results? So we asked before, so if we take the limit as, if you like, you could think of it as h bar goes to infinity. Really, I'm just saying the coefficient of the action goes to 0. So this is a very simple theory, which is simply a uniform measure on the sample space. We're back to just putting all the histories in a bag, picking one out at random. What does it look like? We know by theorem of Feynman and Rothschild that almost every partial order should look something like this.
So this is the opposite of a classical limit when h bar will go to 0.
Sort of, yes.
Right. So what is this supposed to be corresponding with? And is this a correspondence principle type argument or something different?
So maybe for the moment, just forget about the h bar going to infinity and just beta to 0. We can get back to the main questions. So how big is big? So the way to see that is to focus on the height of the causal set. So the height is, again, the length of the longest chain of the causal set. So it's something like the total length and time of the causal set. And so we can ask, how does this distribution of heights for the causal set vary with the cardinality of the causal set? And so here we're looking at the distribution of heights for the first 9 values of n. And so it's a little bit confusing, these diagrams. So each value of n gives a histogram where each color is a different value of the height. And perhaps most interesting will be height of 3, which is given by this dark blue. So as n grows to be 6 or 7, there's a maximum, the fraction of partial orders that have height 3, and then it starts to go down. So we can ask what happens to those. It turns out that by numerical simulation, we can measure the fraction of partial orders which have height 3, and we get this very complicated behavior. You see it as n gets large, say after 70 or 80, it starts to behave like one would expect from the Cosmology theorem. However, we get some very surprising behavior around n equals 32 or so. So the structure of the space of the space of causal sets is somewhat surprising. There was no indication that this would happen. Okay, and then this is the same picture at the log scale. If you look at the difference between the number of maximal elements and the number of minimal elements, this is on I think 58 causal sets of 58 elements. You see that there's something like a peak, which is away from 0. And it turns out that what we find is that, in fact, for naturally labeled causal sets, so causal sets which are labeled based on the order in which the nodes would arise from the growth process, if you look at that set of partial orders, then it's not the case that almost all histories are time symmetric in the sense that the number of minimal elements is close to the number of maximal elements. So there's some hint in which, if you like, the theory could give something like an arrow of time just from an entropy in the set of histories itself. And then the final question about the dynamics, so can we escape from the Feynman-Rothschild orders? So this is a histogram of the, again, the height for a 64 element causal set. So I'm showing in blue what you've seen already, the distribution of heights for 64 element causal sets. We can see it's peaked at h equals 3. And so now we can ask what happens if we send beta to be something other than 0, if we allow the coefficient of the action to be non-zero. And in that case, we can see that we get something that's distinctly different from the Rothschild orders. In fact, the most popular height for causal sets which are described by this analytically continued action with beta equal to minus 0.057 is 5 instead of 3. So the dynamics is able to escape the equivalent Rothschild regime. And then I'll just close with a brief remark that there's some recent. So this is a quote from a recent paper from January saying the current measurements of the low and high redshift universe are in tension if we restrict ourselves to the standard 6-parameter model of flat lambda CDM. So there's some indications from Cosmology that there may be some problems with the usual flat lambda CDM concordance model, and in fact it suggests that the cosmological constant. So a prediction of this way of thinking about causal set dynamics in terms of sequential growth is that the cosmological constant is not in fact constant, but varies and undergoes some random fluctuation. And so the evidence for something like this is building. And so I'll just conclude by going back to my original set of results. So there's some from the pre-quantum, if you like, sequential growth description, and then some from the newer results. The Rothschild causal sets dominate for some n, maybe above 100 or so. It's not the case that almost all histories are roughly time reversal symmetric, so there's some indication of perhaps an error of time from the space of histories itself. The dynamics is able to escape from the Rothschild partial orders. And, there may be some hints from current observational evidence which could lend support to ideas with this form. Thank you. Chris.
I have a really basic question, which is just if you have a space-time that's a solution of the Einstein field equations, and then you have a faithful embedding or a sprinkling of that, what's the relationship between the causal set dynamics that's describing the growth and the dynamical evolution you described for, say, the, if you took the initial value formulation of GR? Are they related in some way, or is the causal set, like generation, the dynamics there, is that a completely different?
That would be the hope, of course. That was our original hope, that the sequential growth dynamics would give you general relativity. It's kind of the most optimistic thing you could imagine. It doesn't, and some of what I said earlier in describing the behavior of that theory in terms of the cyclic cosmology and
Maybe you'd be thinking of the Einstein and the sort of general relativity is maybe an approximate but incorrect description, and the causal set dynamics is really the dynamical law.
Well, that's the idea. That's the end idea. Of course, we don't expect literally. So this theory is classical, the way I described it. It's a classical stochastic theory. So we don't expect it to be the final theory by any means. But it gives some interesting hints about some of the things that we might expect to arise from quantum gravity. One thing I can say on the positive side is that after one of these posts, the early universe described by the expansion of this, by the growth of the causal set, has some properties in common with 3 + 1 dimensional de Sitter space-time. So in that sense...
But there's all kinds of, so just, if I can pursue a little further, sorry, so like the things like the singularity theorems, would anything like that? So when you're talking about the cyclic cosmology, if the dynamics is the dynamics so different from general relativity that when you're talking about the post and the neck, all of the thoughts about singularities and worries that would come in classical GR, those are just inappropriate because the dynamics is so different? Or
So what sort of concerns are you?
Well, I mean, do you have, is it a kinematical effect, or is it a violation of the energy conditions? Why is it that you have a post that then, so in the cycle you don't have a singularity presumably, but you just think
it's a dynamical effect. In fact, it arises from random fluctuations if you wait long enough, well, under the transfer percolation dynamics, by random fluctuations, it will collapse to a single element. And then subsequent to that collapse, you get some early universe, which is just considered like properties. So is that a singularity? Well, I think it's a little bit premature to really say too much more about the connection with continual general relativity.
So the two in the middle of the time reversal symmetry and the Platinum-Rothschild, so those are based on like really, I mean, compared to space-time, small causal sets, right? I mean,
That's
tens
right.
of nodes, right?
Very small.
So how confident are you that, well, you know, you think that they're really indicative of what happens to larger causal sets?
This I do. I think.
Oh, okay, so let's, yeah.
So this, by this, the concrete result is that if you look at the difference between the number of maximal, the absolute value of the difference between the number of maximal elements and the number of minimal elements for causal sets on n elements, when you divide that by n, you get, we expect it to converge to 1/4 rather than 0.
So even if I look at like all the nodes between here and here or something, here and here or something, that'd be a time symmetry, I mean,
Well, so if we're thinking of this as quantum cosmology, and the dynamics is very simple, we're just pulling a history out of the bag and saying this is the universe, then we expect it to be completely time symmetric.
this volume over 1 second or something, the network in there, would I see that asymmetry?
It's possible. Yeah, so right, so that's kind of the idea that some of the things that we're learning here about the structure of causal sets on relatively small number of elements may be somehow relevant for the behavior of physics at small scales.
Well, that's not a very small, I mean, I really mean that, yeah. Like that, this volume of space-time. Like this spatial volume over 1 second.
Right, well, 1 second is huge, so this is extreme.
Well, that's what I'm asking about. I mean, am I going to see the effects of that asymmetry at macroscopic scales?
Well, I mean, I think that's I don't want to overstate the case. So, of course, in the real dynamical law won't be of this simple case. It won't be simply grabbing a history out of the bag. It'll be given by some dynamics such as given by this action that I wrote down at the finite temperature. And so in that case, well, we hope not to get these Platinum-Rothschild partial orders. But I'm suggesting here that there may be another route to arriving at an error of time in cosmology, which is different from the usual way of thinking about entropy of matter fields and so on. So there may be a different sort of dynamical mechanism that gives rise to an error of time, which comes from the structure of the space of history.
You saw some interesting things happening around 32 or whatever it was in your graphs that you had to skip over a bit quickly. Those are finite artifacts of some kind. Do you understand what they are?
No.
32 is about the square root of 100. I've got no idea if those are root n. Where would that scale arise?
Yeah, so you might expect that it kind of has to do with maybe with fluctuation. So one of the things we found is that the way that the Platinum-Rothschild theorem is stated, in particular in a publication by Graham Brightwell, describes the fluctuations in the cardinality of these top and bottom layers, which fall off like the square root of n, roughly. And so, but those are for arbitrarily labeled causal sets, or if you like, unlabeled causal sets. They're almost the same. So what this is saying is that if you impose what we call a natural labeling, which is just attaching a number to each causal set element, which tells you which stage of the growth process it arose on, then the asymptotic form changes slightly. There's still very close to n over 2 elements in the middle layer, but the the probability of what we seem to get is that the cardinality of the bottom and top layers is in fact uniformly distributed between 0 and over 2. So that's where the 1/4 comes from. So, but you're right. So if n is 32, then n over 4 is 8. And so then the square root of 8 is always comparable. It's not too, it's large compared to 8. Maybe that's something that's helpful.
Just to add to that, so the Kleitman-Rothschild paper gives sort of an asymptotic description of the types of causal or cosets that you get. The dominant one for large N is these 3-layer ones, but then the subdominant ones are ones with 4 layers, and then sub-subdominant is ones with 5 layers. And for small n, there are coefficients in front of those, which might make the 5-layer ones or the 4-layer ones dominant. So,
Thank you.
Well, I think it's time for one more question.
Quickly, I was just going to ask how either Hausdorff or the spectral dimension scale and for different arrangements.
Yeah,
So you have this dimensional reduction in that.
It seems intuitively clear that the dimension of these sorts of puzzle sets should be very large. These are very degenerate things. So I imagine if we measured something like the spectral dimension of these things, we would get something very large. So yeah, so of course we want the theory to give rise to something which is smaller dimension, something finite, for example. And so this result that for finite beta, the height seems to get larger at some points in that direction. We're getting something that has some non-trivial temporal extension out of the theory. So that's a necessary condition to get something finite dimensional. But it's difficult to say too much more.
All right. So thank you.